Okay, it's the 12th of February. To go over here and look under quizzes.
Oh, cool. Gives the solutions.
Yeah, the solutions are up now too.
Great.
These are the histograms from the first two quizzes. And there's also a much smaller class. I've talked to one individual, but I don't know about everybody else. It's not here. As a matter of fact, it almost seems even smaller today. No one's saying anything to me, but we're about ready to get into the next chapter, and then things are going to be a lot more fun as far as those sorts of things go. You can go refer to this later, though. This is right here, and the solutions are up here too. The solutions require the password. I reposted the notes for chapter 2 last week on Thursday with a few minor corrections, the things that were brought up in class, but it's not a showstopper. As long as you marked in your notes, it's fine. What I want to do today, though, is continue on with the power spectral density, and then we're going to get into linear time invariant systems. And then what I'm going to do is I'm going to give you a worksheet. It's actually a quiz from last year, but it's a worksheet to try to build some confidence about the convolution and also linear systems, the thing that wasn't so good on this quiz. I think I had high expectations. My grader told me that for the most part, everybody tried to do the convolution, the step-by-step integral, sliding, and all those details. Well, a lot of people did that, though, and that got you bogged down. That's formally the way to do it, but I was hoping that we'd be kind of, beyond that. Not saying that that's not right and just, but if you've seen it done once for two rectangles, then you know how to plug it in the next time. Well, we'll look at my solution, but we'll work this step by step, or at least I'll hand it out when the time comes. Assuming I can get it mounted on the desktop here. So there's the last three. There's 3 people and there's 3 quizzes. That's got to be you guys.
Yeah.
I'm not disappointed. I mean, it's a match. So I'm happy. Okay, so I'm going to go back to where I was here. I'm also going to show you something in MATLAB too, as opposed to running it in ADS, which is what you do in the lab, but it's just to show you some variety. So I guess I was going to go look at the quiz, just to give you an idea of what I was thinking of, but obviously I'm learning my lesson that what I'm thinking of is not what you're thinking of. So in this first problem, I looked at it and I said, well, the first thing is even, odd, it's neither, right? It was kind of an exercise in seeing if you were paying attention, because the triangle in the middle is definitely even, and then the 2 rectangles that are staged on the outside are odd. But when you combine those 2 together, you've got a neither case. So then when you jump in to take the Fourier transform, there's really one theorem that you use and then 2 transform pairs that you use. The transform pairs are the rectangle and the triangle, and then you have to use the delay theorem on the rectangles that are shifted to plus and minus 6. So actually this is at 6, that's centered at minus 6. So that gets you, well, I guess the first step is to just write it out in terms of the special functions. the two rectangles, shifted plus and minus 6, the triangle, and I had a typo in mine, and the grader found it, and then I didn't correct everything.
Should the triangle be double the amplitude too?
Yeah, she fixed everything. I was in a hurry as usual, running from editing books to coming to class. So there's another 2 in there. So there's supposed to be a 4 somewhere. A 4 over here, right? Mm-hmm. Yeah. I'll have to scan this again and repost it, because she told me all about this over the weekend when she was grading it. So there's a 2 on the triangle, and then there's the 2 rectangles, and then from the delay theorem you get an e to the plus j because of the plus sign right in here, and then the minus sign in here gives you the e to the minus j over here, and you bring those 2 together, and because I had the sign error on there I got a cosine, but you have a minus sign in here, so you have an e to the plus j minus an e to the minus j, which is the setup for a sine, right? So to make it complete, I put the 2j in the denominator, and then I put a 2j up in the numerator, and then I convert that to a sine. That wasn't strictly, I was looking for you to get it simplified. That was just to get it polished up and a little bit cleaner looking. So that converts into a sine, and then there's a 2j that comes out and joins with the 2 from the sinc function itself, so it's a 4j. So actually, if you look at this as 2 different parts, this is from the part of the waveform that's the odd function, right? Everybody agree? That's from the 2 rectangles. And that's a piece that's an odd function, and sure enough, that is a purely imaginary Fourier transform. So the symmetry property holds. The triangle is the even one. That's the 2 sinc squared of 2f. But when joined together, it's complex. The second one is where you had is where doing simplifications had come into my mind. At least that's what I thought of. And I set this up on purpose because I said everything we've been practicing with has been the rectangle convolved with the rectangle. So I said a rectangle of base width 2 convolved with a rectangle of base width 2 is a triangle. So the idea is that you've got a superposition. Oh, pen's going crazy on me. Superposition of a rectangle there and another rectangle there. So if you break that apart from the hint, you're doing two convolutions. Get this bigger again. Doing 2 convolutions, x1 with the first pulse and then x1 with the second pulse. So that's these 2 convolutions in here. And with the exception of the delay, it's just rectangles of the same width too. So this was my, maybe you might call that a cheater step, but I was calling that legal because of the fact that that was worked in class, and we talked about it. It's in the notes. But you can just use that in general. I mean, but that's maybe where we need to talk, what the confusion could be. As long as you convolve a like pulse with a like pulse, in this case the rectangle, you're going to get the triangle. The time offsets can be sort of pushed to the background and just taken into account later. You don't have to deal with that right now. You can pretend it's an on-shifted pulse, and then the shifting just gets applied after you get done with the transform, or actually when you get done with the convolution. Now I don't know if that was a barrier for anybody or is a barrier, because I'm willing to answer questions or just talk about it.
I guess it's more of a request than a question. Do you think we could get one of the Fourier transform tables, like from in the book, used with this as well? Because that caught me out. I think I would have been able to spend more time thinking about the concept of the problem. I wasn't trying to remember what the actual, like whether multiply by tau or divide by tau, and where the pi is.
Oh, you're talking about for the pulses?
Wasn't that Steven right?
I gave you the Fourier transforms.
Yeah.
Oh.
Are you the only one that didn't look on the backside?
I had no idea that was one of the
Really? I thought I said I gave you tables, and when I said tables, it was plural, so.
Yeah, it's fine.
Okay. Sorry about that.
It's not your fault.
Well, maybe it is. I don't know. Does it require, should I have had one of two on the bottom of the first page so you knew that there was a second page?
That could help.
No.
Only so much you can do.
Okay.
No, it wasn't right.
I thought what you were saying, Robert, was that you wanted to have the definitions of pi and triangle.
Oh,
That didn't matter to you.
no.
Okay. Okay. I would have liked to have put them all on one page, and I could have done that, but then they would have been more miniature, and I decided, I like to have it bigger. At least, now that I have these powerful glasses that I wear to see up close, it's like, okay, I can read small stuff, but bigger is still better. Okay, so the the rectangles convolve and get rectangles, but it's based upon, this is the underwriting property in doing the two convolutions.
What's that support check?
Support check was what I talked about in class, saying that support is a mathematical term, but it's saying where does the convolution exist? Where is it supported on the time axis? Where is it non-zero? And the support interval is supposed to run from the sum of the two starting intervals, two start points, to the sum of the two end points.
Right. Okay.
So I looked at this and I said this guy starts at -1, okay? So this pulse starts at -2 and ends at 0. So I take -1 and -2, and that makes that guy start at 3. And then this one ends at 1, and this one ends at 0. So that's the 1. And then the second pulse starts at 0 and ends at 2. So that's -1 and 0. I feel like I'm better prepared once my book gets published, because I didn't have some of these things in the book, but then I kind of laid it out there, and now it's laid out crystal clear, I guess because dummies books are supposed to be so, for dummies, so simply laid out. It's been beat into me now by the editors and I feel bad in a way, but help is on the way, I guess, in that sense, because there are little checks, and that check for me is just to say I know where it's going to be supported. In this, when I say supported, I'm talking about -3 to 1 and -1 to 3. That's the notion of support. I didn't come up with that. It's a mathematician's term. And they made me take it out of my book because they said that's too abstract. I had to come up with some other more common-sounding language, but I still like the term support. It's like literally holding something up, is what the idea is. It's held up here, and it's not held up over here.
From going from the picture on the left to the picture on the right,
Mm-hmm.
you just sum the, or is there any easy way to go between those two pictures other than, because I have a tough time
Okay.
visualizing that sum.
Does anybody else want to offer their suggestion? I'll throw mine out there. Mine's pretty easy, but
I just connected the peaks.
okay. And why does that work? What's your proof of that?
It just seemed like it was a bit higher. I have no
Okay.
no pressure.
Well, somebody else have an idea. Somebody that's thinking mathematically.
Well, if you can superimpose functions, you can superimpose points. So in sense that if you can add functions that way, you should just be able to add their individual.
And if you're adding two lines together, what do you get? If you multiply things, you can get strange things, right? But if you're adding two two lines is going to be another line. If you added a curve with a line, it would be a curved line, and so on. So I think that's. Does anybody else want to offer a suggestion?
I think in terms of look at what the slopes are, and if you add the two slopes, then you know what the slope of your final thing is. So So
Yeah.
one in both cases, so you had a slope of like a rise of 2 and a run of 1 or whatever.
I'm probably guilty of high expectations. That's kind of the way I live my life a lot of times, and that's pretty dangerous actually. But I'm sure some of you do that too. If you're, I mean, I haven't been skiing for a couple of years, but if you snowboard or something like that, some of you probably are living on the edge when you're out there skiing or something. So that same idea applies to engineering. You can kind of live on the edge. You want to have safe designs, but you kind of go out there. And I guess I'll just say I worked on my master's degree at Michigan Tech. I worked for a man who was a real hands-on electronics designer. He came from Motorola Government Electronics. I think I told you that is now General Dynamics down in Scottsdale, Arizona. He taught me comm theory. He probably reviewed this because he taught out of this very book. Only it was the first edition of the book that I learned out of. He was the kind of guy that would go build things in the lab. He would have me do PCBs and solder things up, and he'd go to the lab and test it. And then he'd sit there and figure out the math later. Is anybody in here like that? You like building things and then you go back and figure out the math later?
Yeah.
Chances are you're going to be more interested in hardware design than you are theoretical modeling. That's just my experience. I mean, that's the way I started my career. I was a hardware engineer, and then I got into systems modeling when I got my doctorate. But that was me exactly. I did schematics, had boards laid out by the board layout people. Then I was at the bench getting my design to work and integrated with the other designs of systems, and didn't really want to do much on paper with math. I just wanted to get a design that would work. And you know, a lot of electronics was that way. I don't think today you quite that seat of the pants. You use SPICE probably a lot more. I did not use SPICE. I just did hand calculations to bias devices and things of that sort. Can't get away with that, I don't think, anymore, or get away with that. But same idea is kind of applying here, the linear line segments. So I drew my picture on the left, and mentally, here's what I did, is I looked at it and I said, okay, those 2 points, 0 and -6, so that gets me that one. I know 6 and 0, that gets me that one. I'm confirmed that that's -3 and +3, and then your mind's eye looks at it and says, okay, it's going to do that. It's going to hit those other points. There's a limit to that, though. You can get into trouble, and I'm willing to guess that maybe in calculus at some time or another you might have dealt with something with function plotting where you might have had something like this, and the question is, does it do that or does it do that? Have you ever been confronted with that? It's like, I can't figure it out. Then I would plot a few points to make sure. Or if you're standing at the whiteboard because you're having a technical interview, those are the types of questions, silly little questions that sometimes employers make people stand at the whiteboard when they're being interviewed, and it can be really simple things like that. If that's something that they're interested in testing you on, and why interviewers ask certain questions in a technical interview, it might just be part of a game too. Can this person do that or not that person? I mean, I've just heard stories about things like that. So at any rate, those are the two pieces. But there is yet another way to do it, and the pure Fourier transform method would say we can do this in the frequency domain. So if we work it in the frequency domain, you're going to be taking and finding the Fourier transform of that multiplied times the Fourier transform of that. So that's what I do down here. I have the 2 sinc F2F, that's the X1, and then the 2 pulses, each pulse gives me a 6 sinc 2F, and then again from the delay theorem, just like in the first problem, there's an e to the plus j and an e to the minus j standing out there. In this case, you don't want to convert that to a sine or a cosine or anything like that. You just sort of hang out with it for the time being. And you go down to the second line, though, and you combine the two sinc functions, and you get the 12 sinc squared 2f. Now, that tells you right away that that's a triangle, because we saw last week that the triangle in the frequency domain is sinc squared, right? And you kind of knew that was going to happen anyway, but this just sort of puts it up in a different mode where you can see it right in the frequency domain. And then when you go to inverse transform to get back to the time domain again, you're better off just leaving these two terms as they are, because they're multiplying the sinc squared, and that's the delay operator in the frequency domain. So you just look at the sinc squared 2f, you know, goes back to a triangle, and it's going to go back to a triangle, you know, triangle of t over 2 because of the 2 here. But then you uncover that and say, oh, the e to the minus j, or minus e to the plus j, that minus sign is going to come down into here. And then this is a plus j, so we know that a plus j comes from something that was shifted to the left. So I put in a t plus 1, because there's effectively a 1 sitting over here, and there's effectively, I guess if I combine that, there's a minus 1 sitting over there from shifting to the right. So that gets you there too. I left it open-ended because I wanted you to decide what to do and what to try. Did anybody do it in the frequency domain? Did you get it right?
Yeah, I forgot about multiplying it by 3, just because I made a simple mistake.
So you had a scale error, but other than that,
Yeah,
okay.
I got it right.
What led you to want to do it in the frequency domain?
Because I didn't want to do the intervals and
Okay.
and I
So-
was kind of limited on time, so I just had to do that.
Are you the snowboarder that takes the crazy moves too?
I don't take crazy
Leave
moves,
dangerously?
I do snowboards.
Okay, I'm just saying if there's a correlation.
Yeah.
I don't know if there is or not. Okay, well, if that's not enough, because I have such a meticulous grader, she sent me her notes on how she looked at it for grading it based on what she saw that she had to grade. And I don't know if I can afford her anymore, but she spent 5 hours grading just this number of quizzes. So that was a lot of time. I also have hired her to help me with the editing marathon that I'm in this week, and she's doing well at helping me with that too. So you can go take a look at what she wrote down here. I think she was inspired to write it up this way because, number one, she's reviewing things for herself, even though she just passed the qualifier for the PhD program. And actually, she probably reviewed all this stuff before she took the qualifier. And she was trying to align with what some of you had done on the quiz. So this little handout that we'll go through later is going to be the same type of thing, only it's a somewhat different problem. So any questions before I go back to the notes and get into linear systems? Okay, last time we were talking about autocorrelation function and then the power spectral density. So the fundamental result from last time with regards to power spectral density is that the Fourier transform of the autocorrelation function is the power spectral density. And the only way to really get the power spectral density, which applies to a power type signal, is to come through the autocorrelation function. There's really no other way to get there, except something that I'll show you a little bit later. You can get there through the Fourier coefficients. So there is sort of a back door, and the back door would be to come around. This I'll get to later, would be through the xn coefficients, and that can get you there too if you happen to have the Fourier coefficients right there. I mean, and that's the thing. Do you have them handy or not? But then you remember that nice little theorem, which can make it easy too. So there is an alternate way, and it's actually kind of amazing that you can actually go backwards to get the autocorrelation function. So if you can get into the power spectral density through the back door, that means you could, if you needed to get that, you could get back to that by that way. That's kind of seems awkward, but the reason why that may present itself to you is because of the fact that the autocorrelation function is kind of like doing a convolution. So it's not exactly a real fun thing. This thing is stuck right now. It's weird. It's acting very weird. It actually went back to the very beginning. Probably because I'm running the recorder. It did something strange. I've never seen that happen before. Let's see, I need to go way down here. I must have reloaded something, I don't know. And what I wanted to do is just look at the autocorrelation function. Oops, it just did it again. I have to get after this German guy. This software I'm using comes from Germany. It's shareware, and maybe I'm having a problem with my shareware. I showed it to Dr. Trimboli last year, and he bought into the idea of using it too. So we already did that. Okay. So there's the time average autocorrelation function for a periodic signal, and that's like doing a convolution. So it's a little bit not that much fun. We looked at properties last time. We looked at the single sinusoid, and this was physically satisfying because it's two delta functions. It was just a squared over 4 at the two frequencies, and when you integrate through that to get the total power, you do get a squared over 2. And that was satisfying. Remember, P average is the power spectrum integrated. And in this case, that's going to equal a squared over 2, which we know is the power in the sinusoid. And that's also equal to, now the other way of getting that from the properties just down the page is Rx of 0 is also equal to the power. And so if we set tau there equal to 0, we get a squared over 2. That's just two ways of getting there from the autocorrelation or the power spectrum. These two properties I mentioned are useful for time shifting and amplitude or level shifting up and down, and they mostly apply. They're mostly are applicable when you're doing measurements. At least that's where I've found them handy, like in the lab experiment that involves the PN generator. Okay, what about two sinusoids added together? This is pretty straightforward and pretty logical, but it'll show you some other utility in this analysis. So you have two sinusoids, they're at different frequencies. We don't really care about the phases. The phases on the sinusoids can be anything. It doesn't matter. It won't change the power spectrum. However, I could pause and say, why do you think that is? Well, we have this property over here that says it's blind to a time shift. And a time shift and a phase shift on a sinusoid way back in 2610 are equivalent. Can you remember way back to that point in the very beginning? So that tells you phase and time delay in a sinusoid are the same. So if a time shift, the autocorrelation is blind to a time shift, it's in particular blind to a phase shift on a sinusoid. And when you take measurements with a spectrum analyzer, you definitely know that's the case. But here we have two sinusoids at different frequencies, so we plug into the autocorrelation function just using the definition that involves the time averages, these left and right angles. So this is how you can take advantage of this shorthand time average operator notation. When I go through this operation here, I've got x1 times x1 shifted, and then there's a plus sign missing in here. I just realized that.
So you said that the time average was integral?
Yeah, the time average is, for a periodic signal at least, I'll write it down like that, it's x of, well, it's whatever I plug inside of here. Integrated over a period, if it's a periodic signal. In general, though, if it's not a periodic signal, then it's a limit. So you have to change that into a limit. And that was quite a few pages back, but Dr. Zemer puts it in the book because he's trying to just have a shorthand notation to avoid having to write down that integration. And we're going to be using time average in Chapter 3 a lot. It's just a quickie notation that brings understanding. Now, what is the time average of a quantity? It's the average value. And what is the average value? The DC value. So really, you can just think of the time average operator is pulling out the DC value of whatever is inside the angle brackets, because it's averaging out time. So in this case, with the plus sign added that I forgot, we've got x1 times x1 delayed, x1 times x2, and then x2 times x1 delayed, and x2 times x2 delayed. So there's 4 terms that come out. It's kind of ugly looking, but that's what happens when you have 2 terms times 2 terms, right? It expands out into 4 terms. The first and last terms are special. Actually not first and last the way I wrote it down here. These 2 terms are special. x1 times x1 delayed is just the autocorrelation on x1 by definition. The second one is just the autocorrelation on x2 by definition. The last 2 terms, though, are something that we really haven't dealt with. It's an x1. It would be called formally it'd be called a cross correlation between 2 signals, because we're crossing one signal with another. But we can actually discard those terms in this case, because x1 is a cosine at f1 and x2 is a cosine at f2. And when we take cosine times cosine, we get, at the output, we get 1/2 cosine of the sum plus 1/2 cosine of the difference, right? That's a trig identity. If you don't have that in your brain right now, in Chapter 3, it's going to be like you're going to have it memorized again. It's just one of those that, for comm theory, it's really vital. You can look in the appendix, though, and see. So as long as the 2 frequencies are not equal, that says that this cosine has an argument that is not 0. Okay, so it's a cosine at some frequency, either the difference frequency or the sum frequency. So what happens if we average a cosine over all time? It's always 0. It's pretty handy to have that go away. It doesn't matter how close they are to each other, as long as they're not equal to 0, it's going to average out to 0. So if you were thinking spectrally on the frequency axis, that you have a cosine that shows up as a spike here at, suppose that's f1 minus f2, just take the absolute value of it. Suppose that's getting really, really close to 0. As long as it's not 0, the average value we're going to see in the next section is like applying a narrowband filter that just lets through whatever the DC value is. And as long as that spike is not at 0, the averaging operation throws it away. We'll have that interpretation as soon as we go through filters more clearly. I'm sort of riding on your past exposure, though, to linear systems, but we're going to review through that here later today. So it's just the sum of the two autocorrelation functions, which is what the answer is. And then, of course, the power spectral density would be the superimposed spectra from each of those Fourier transforms. Again, as long as F1 does not equal F2. And if F1 equals F2, then just like in 2610, what would you do then? If you can think back to that class.
You just add the amplitudes and the phases.
Right, what was that
Keep the
called?
same frequency.
Phasor addition formula, do you remember that?
Yeah, something like that.
You don't want to forget that one either.
Oh, okay.
And you've actually you've come through that in circuits too, because that's steady state AC circuit analysis relies on that too. I don't know if that ever kind of became obvious when you first saw it in 2610. That was meant to be like a precursor to what you would do later in circuits. It's funny how things are when you're in the midst of it. You don't understand that that was laid out there as a foundation. You don't see it as a foundation until years later, but it was there for a reason, actually. So you'd have to add them vectorially, like you just said. You'd add the amplitudes and the phases, so you'd end up with something like A1 e to the j theta 1 plus A2 e to the j theta 2. You'd add them vectorially or as complex numbers, because that's what the phasor addition formula told you to do, right? A long time ago. Okay, we talked about the PN generator last time. This is used for random numbers, and like I said, this is used in GPS, for example. Two M-code sequence generators combine together to form gold codes, and the gold code sequences are used in GPS for the course acquisition code, as they call it. And that's the commercial part of GPS. The military part uses a P or a Y code, which is a classified code. And we never see that unless you're in a military mission, but commercial users use the gold codes, and those are related to the M sequence generators. So this is what the generator looks like in discrete logic. It puts out a finite sequence. The logic that I've got defined here is bipolar logic value, so I've got plus and minus A, which is more along the lines of what comm systems analysis people use. But in reality, logic values are, like 0, 1. It would be an artificial value, but if you're talking about CMOS or, in my day, TTL logic, it's going to be something that rides above 0, right? Close to 0, and then to some VCC or something like that.
So is the pattern for this one 1, 0, 1, 1, 0, 0? Is that what we'll always do?
For this particular sequence, which has got 3-stage register, so that's 1, 1, 1, 0, 0, 1, 0. That's the pattern. It's 7.
So are ones stored in each of the
D flip-flops? Yeah.
initially?
Mm-hmm. And a property of an M sequence generator is it will always have one part of its cycle that contains as many ones as there are shift registers. So in this case, a pattern of 3 ones in a row occurs just once, and then there's a pattern of 2, and there's a whole bunch of statistical theory about PN generators that comes out. The generator can never have all zeros, though, because then the XOR gate would die. The generator dies if that happens. It stops working. So it has to start with some load, otherwise it will never get started. I built these in electronics, and when I worked in industry, there was like a startup circuit. This was back in the olden days, and you would have something that would make sure the shift register, when it turned on, it would never get faulted, so that it would push some ones in to get it started. It was kind of like kick-starting the generator. If you didn't do that, it would just sit there and put out zeros, which was not too good. Companies like RT Logic and Emergent, where I do work now too, they use these for pattern generators for doing what's called bit error rater testing. So these are very common. The M sequences are very common. PN is pseudo-random, by the way, if I haven't made that clear, but M is the more mathematical terminology, M sequence, which means maximal length sequence. The maximal length you can get with that many generators. And I have a MATLAB function we're going to look at here in just a second. In terms of getting the spectrum of this signal, this is where the power spectral density comes in handy, because Fourier transforming a whole period is pretty intimidating. The properties of the M sequence are such that it has this as its autocorrelation function. And this takes some proving, and it's not something that I'm expecting you to know how to prove. It's just, it's given to you because they've been evaluated. You can show this, though, on the computer. So it peaks up at a squared, if the amplitude's plus or minus a, when it's perfectly aligned, when the two patterns come across like this and perfectly align, and then as soon as it starts to slide one side or the other from alignment, the lag we talked about last time, it immediately falls down to minus a squared over m, and it holds at that value until you slide one whole period and get within 1 bit away from the next peak, and then it starts to climb back up again. Interesting property, though, is for m large, what's going to happen to this autocorrelation function? When m is large, in other words, m is the number of bits in the period. When m goes large, that minus a squared over m gets small. If you had a truly random sequence of bits, like a truly ideal random number generator that never repeated, it would just be the triangle. It would just be something that it would be uncorrelated as soon as you slid 1 bit away from alignment. You would see no correlation. That would be the perfect random sequence. But guess what? The perfect random sequence never repeats. So if you're using that in a comm system, how would you get the alignment back at the receiver? In other words, somebody transmits a message encrypted with this so-called spreading code or random sequence. This is the beginnings of spread spectrum for military, and it was kept a secret for a long time, and then it eventually ended up in commercial products. But if it was so long that it never repeated, how would the local receiver know how to align itself with that code? Because the basic property of the PN code is if it's plus and minus 1s and you multiply by that same code back at the receiver, you strip that code off and you're left with whatever data you might have sent underneath it. That's the basis of covert spread spectrum. You'd have a data pattern, you multiply it by the PN code, literally multiplied, or XORed, I guess is another way of thinking of it, and then at the receive end you re-XOR with that exact code. When it's perfectly aligned, it strips it off, and you're left with your data. This was a military secret quite a few years ago. Yeah?
So basically, if you increase m, you
Make it more...
increase the amount of randomness in the system, but
right.
At the same time, you trade off because you're going to lose kind of being able to receive.
Well, the period...
Increase the period, so it's
and
less
then
periodic, and then you can't receive it.
You can receive it, but you have to search for a long time. Locally, you don't know, so you'd have to just start searching until you get the alignment. But what the military did and what your cell phone does, like remember I said your SIM card on your cell phone has an offset that it knows if you have a unique offset over this very long code that I'm thinking is a month long or something like that in its period. Searching by just stepping along, trying to find the alignment would take a long time, so it knows, the base station figures out from your ID basically what offset it needs to use when you're talking to it. Likewise, you know what to use as an offset when you're talking to the base station. Actually, the base station talks on with a different code than what your uplink code is, the one that it needs to have knowledge. It needs to know the offset. In the military scenario, the way it was explained to me is like an aircraft would take off from the base station. It would be, they program in this code offset, and then they would fly, and then when they wanted to communicate, they would just engage their code because they had it running after a hot swap, so to speak. They knew the code alignment and they knew the drift rate, so then they could sweep through the uncertainty region. But in other systems like the GPS, which uses the short 1023-bit long pattern, you can search pretty quickly. But in really covert systems, that is an issue, how long you have to search and how rapidly you can search. So they have what's called a bank of correlators. So they just don't have a single autocorrelation going on, they have multiple. So they're doing parallel processing to just kind of find it. Is that interesting? It's been, you know, foundational in wireless communications to be able to do that. Search using a random code, and that's kind of why I got off on having you explore it in the lab too. So here's some software. I was going to run a little MATLAB demo here. These functions are on the website. So I have, this is the PN generator code right here that just basically further on in the book, and I forget what chapter it is. You know, is it in chapter 7? I taught COM2 last semester out of this book, so I should be able to find it. There's a section on spread spectrum, so you could read about that. But prior to that spread spectrum section, on page 507, there are pseudo-noise sequences. And then he's got a table of different connections, exclusive OR connections from the shift register sequence. And I went out and just got some additional ones. So some of the scoop on this is up in chapter 9 at this time. And then spread spectrum is the next topic that's talked about. So I picked different taps, and then I built a wrapper function called PN source that sits on top of that. And what it does is it makes a waveform out of this. If I just call M sequence, it just gives me a sequence of 0, 1, 1, 0, 0, 1, 0, 1. If I run it through this function PN source, it stretches it out, and I can define how many bits I want to put out and how many samples I want to have per bit, as if I'm doing this in discrete time signal processing, which in MATLAB I am. And then M is whatever value I want to have for M, like 3 or 5 or whatever. So got it set up here. I'll just put in the 3-bit one, and I'll put in a really short sequence, just 100 bits. And I'm doing 10 samples per bit. So if I go ahead and plot that, oops, I didn't redefine my t vector. I just put a time axis on here. So there's the pattern. If I axis in on that to say just do 20, that's the same pattern that we were seeing in the notes. It's just a piece of it. It repeats over and over again. Because what I did is I repeated the cycle when I called the M sequence generator. It gives you a vector that's just one period long, but then I concatenated those vectors and did some digital signal processing to get it stretched out to look like a waveform. Make sense? So then jumping back over here to the notes, we have to look at what is the what does the spectrum look like, and that's discussed in the homework problem, which, you know, I've given you the solutions, and this is to help in the lab, but also give you another waveform to look at finding the power spectrum of. We can use this Fourier transform theorem, which says that we just look at one period of the autocorrelation function and Fourier transform that, and we end up getting sinc squared, because when you Fourier transform a triangle, you get a sinc squared, right? And then you're sampling it because it's periodic, so you have this NFS plugged inside of there. And when you put it all together, this is what the spectrum looks like. It's sitting on a pedestal because it's not sitting on 0, it's slightly lowered below 0. So there is an extra little factor thrown in, and that's based on the model here. I don't really want to dwell on that a whole lot, because those of you in the lab, you get to wrestle with that, but you can refer to the solution if you want to. But over here in this domain, let's just see if MATLAB holds true to that. So what I'm going to do is I'm going to go back to my longer length vector of 10,000 symbols, and I'm going to take my t-axis back to that length. I'm going to plot it. It's very dense. I don't really want to do that so much. What I want to do, though, is go back and do the spectrum on it. So I've got another window open up here that has something that you'll be using later in the class, a little function called simple spectrum analyzer. So I'm going to do a 2 to the 14th length fast Fourier transform to approximate the power spectral density. I'm going to tell it that I've got 10 samples per bit so that I get it normalized to the bit rate. And I'm going to display it from minus 80 dB to 20 dB. So there's my line spectrum. That's a line spectrum. It's just pretty dense. You'll see that in the lab, though, for those of you in the lab. I may have plugged, oh, this is the 8-stage guy. So let's back out. I did the wrong one. I wanted to make this be 3. Now I'll do simple spectrum analyzer on that. Okay. So the spectral lines are not that close together, because the spectral lines from the math over here, let's see, the spectral lines are spaced at 1 over m times, and m is actually not m, it's 2 to the m minus 1. So I think I've got kind of a confusion factor in here. So it's 7 in this case. So it's 7 times the period. 1 over 7 times the period. So the spectral lines are going to be spaced at that amount. And then if I make m get bigger by increasing n, the number of shift registers, take it up to 8, which was the other example that I was in the midst of running here. Put up another plot window. And I'll let that be 8. And then I'll do the simple spectrum analyzer. And that's quite dense, but it is not continuous at this point. If I zoom in on that, and that's why I'm using such a large FFT, 2 to the 14th. What is 2 to the 14th anyway? 16,384 points in the transform. So I'm trying to get more resolution in the frequency domain than the resolution of that I need to look at this spectrum. So if I go zoom in on it, for example, and I'm trying to get, there we go. This is the newer MATLAB interface. Is this running in the labs now or not?
I don't think
This is 2012B, the one that came out in September. Okay, I'm zooming in on the main lobe of the sinc function, or sinc squared. Let me zoom in on it some more. Now we're starting to see that there are spectral lines there. I mean, it's not a delta function exactly because I'm connecting the dots, but if I was to go look at the line spacing by zooming way in on it, and I could still use some more FFT resolution. In the lab, you have spectrum analyzers that can zoom way in, so you'll be able to just zoom way in on it. This guy, I've got to increase the resolution by taking the FFT size up to, say, 2 to the 18th. Is anybody curious about that and onto itself? Or is this, I'm just basically plotting the spectrum, and I'm using a tool to estimate the spectrum. I'm not actually doing a mathematical, theoretical spectrum with the sampled sinc squared. I'm just using the FFT to estimate the spectrum. That's the function I'm calling simple spectrum analyzer is using a method called the method of averaged periodograms, which just takes the records and averages them.
Is that faster than the FFT function?
This is the it does use the FFT.
Okay, so
It's kind of beyond the scope of the class for me to give you the details on how it works. Just call it the magic spectrum analyzer function that approximates.
I'm just wondering why you use this instead of like FFT.
Okay, that's a good question. So Rob's question is, why don't I just take and go FFT of x like that, right? It's gonna, yeah, there's gonna be a shifting business between the low and high points, and then I'm not going to get any averaging over the pseudo-randomness, and I'm going to get something a lot noisier. This simple spectrum analyzer does the time averaging to make it look like the real Fourier transform of the autocorrelation function. So it's doing more things behind the scenes, things that I can't take time to explain right now. I've got it written into my COM2 notes to explain how this works, but it blocks up the data, and then it does some averaging of sub records, and just you have to accept it on faith right now that the math is good, but it does require lots of data to do well. So let's back up a second. Since I'm curious, I'll take this up to 2 to the 18th and run it. And now if I zoom in on this, now it's definitely, now it's a lot sharper looking. It's still not very regular because of the way the averaging is being done, and I could feed in more than 10,000 bits if I wanted to, but you get you can see that it's not continuous. It definitely has a structure to it, and it's related to the period of the generator, because it's a periodic signal, and what do we know about periodic signals? The spectrum is not continuous. They have spectral lines related to 1 over the period. It's always going to be there. Okay, a little analysis that I threw in here that I'm not going to spend time on, but I just threw the math in to say what happens if I start from the Fourier series for a periodic signal. I know that there's a Fourier coefficient xn, and if I then cram that representation into the definition of the autocorrelation function, I've got this kind of messy thing here that I'm going to take the time average of, and I can establish the fact that the autocorrelation function can be written in terms of the magnitude squared of the Fourier series coefficients. And so if I Fourier transform that on both sides, I get the spectrum, and then I get that the magnitude squared is the power spectrum. Magnitude squared of xn of f. Remember, last week we were looking at, for a periodic signal, just the spectrum, not the power spectrum, but the spectrum was, well, this is going to the power spectral density. Remember, a while back I was showing the backwards path was, or the backdoor path was to come in at it from this way. And the other thing that we learned last week was that xn is equal to f naught times n f naught, right? F naught is the period, or f naught is 1 over the period. So this just gives you another route to get to the power spectrum for a periodic signal. Still without doing a whole lot of heavy lifting, because you can just get the Fourier transform of one period and then use that theorem and then come through and have the spectral lines as being the magnitude squared of xn, which would be the magnitude squared of this quantity right here. Is everybody falling asleep on this? Or, I mean, it's all mathematical, but it's all kind of what COM theory is. You gotta have the mathematical tools to do the stuff.
So you could do the magnitude of the frequency squared times the pulse of n f naught squared, essentially, instead of the Fourier coefficient.
Yeah, I think this is what I was thinking of. That could be equal to the magnitude squared of f naught
Okay, yeah.
exactly.
So this whole derivation's, I mean, for just this page, is just another way to get into power spectrum?
Yeah.
Okay, so it's just a different derivation.
If it's a periodic signal.
Right.
Now, something that's being left out of here, and this maybe gets back to your question, Rob, about why can't I just take the FFT? The power spectrum, because I am taking the FFT, but the power spectrum applies to both random signals and deterministic signals. So if it's a random signal that was noise and signal together, then the Fourier transform of the autocorrelation function gives you the power spectral density. The lab instrument does that. This function, simple SA, will do that properly. The FFT will not do it properly. It will get you a random spectrum. I mean, if you take a random signal in FFT, you get a random signal in the frequency domain, which is all over the place. It's very noisy looking and not settled, whereas the power spectrum is a deterministic function after you take the limits and such. It's right on the edge of what you can do in this class, though. It's kind of like we're just trying to establish it and then move on and finally get into the COM theory part. But it gets picked up again in COM 2, the random signal idea. It's because there's no prerequisite in this class for probability and random variables. Because some of you are just taking it right now, and I have to take you beyond that to get into random processes. And it is pretty ugly stuff. But again, it adds to this, and some of you are going to want to go on and capture that, because when you're in the lab, like at RT Logic, you're working with signals that are deterministic, and plus you have a noise generator that's generating noise to simulate the electronic front-end noise. Put that in, you see it on the spectrum analyzer. You can explain the spectrum of the signal, but how do you explain the spectrum of the noise? That takes the next step, which is the random process modeling, which is left out of this class.
Basically, you use power spectral analysis when you know you have a signal that's that has noise that isn't necessarily relegated to one part of the spectrum. It's all over the place, like with Gaussian noise or something like that. And this is the only way you can recover. You can almost recover your.
Well, you can analyze what's going on, and Gaussian noise is just one probability distribution. Uniform could be another type of noise. If the noise is white, is what means it covers all the spectrum. White noise spectrum means it covers all frequencies, because white light is composed of all colors of light, right? Colored noise is where you only have it selected bands of frequency, and hence like purple or green or something in light. That's the analogy. We're not really going there either, because that requires a random process modeling. It's probably scary to say, but it's just the way it is. I mean, that's one of the things that's why you're in this class, though, because you're willing to kind of go the distance. Did any of you take control systems last semester? That kind of goes down the other pathway. This goes down the Fourier series and Fourier analysis, whereas the controls, didn't you spend a lot of time with Laplace, using that for everything? And most people enjoy Laplace transform math a whole lot more than they do Fourier. But still, if you drive controls hard enough, you get noise and need power spectra and autocorrelation and all that stuff too. So they both are pretty mathematical. And signal processing is the third leg of the stool, in my mind. Digital signal processing is another part of the whole business of signals and systems beyond the basics. So there's a three-legged stool: COM, DSP, and controls. Okay, linear time invariant systems you learned about starting in 2610 and then more in 3205. You apply an input to an operator, call it H. If it's a linear system, then you have the property that the superposition holds. So a linear combination of inputs is the same as the linear combination of the individually obtained outputs. So this is, putting the whole thing together and operating on it. And then if the system is linear, you get the linear combination of the individual outputs. That's the linearity side of the definition. The time invariant side says that the system does not change over time. So I apply an input now and I look at the output. I apply an input at t0 seconds later and look at the output. And with the exception of the offset t0, the system has behaved identically. It's just the offset is just because I applied the input later, but the system hasn't changed over time. When I'm trying to get people to understand time invariance, I think of if you built an amplifier in the lab and it was at room temperature, it would be fixed in time because it's not going to change. But if you take it outside on a hot day or a cold day, the device is going to change some of its properties slightly, so it will not amplify with the exact same magnitude and phase shift at all frequencies just because of some changes in the circuit. That's kind of a gross sense of time varying, and aging. I always think of the example of the cable TV network has got those green boxes around the city, and they have to have some good insulation on some of those electronic boxes because it does get cold out, and maybe they have heaters in them, I don't know. They power little heaters to keep them at temperature so that they stay operating properly. But that's the idea of time invariance. The properties of the system do not change with time. So the linear time invariant model then goes on to say that if you want to characterize the output of a system in terms of the input, we generally work with the impulse response. So the impulse response is a special system output. If we take a linear time invariant system and apply a delta to it, oops, my touch screen is all of a sudden, it's like it's hypersensitive. Apply the impulse function and have the system initially at rest, so the output of the system is the impulse response. And again, to me, the impulse response is just like a characteristic of the system. So if I could measure the vibrations on my water bottle of plucking my finger against it, that would be like giving it an impulse, and then the vibrations that it would set off could be recorded as the impulse response. Only this is the electronic circuit equivalent, because an impulse is like pinging it with a delta, and then it rings or does something, right? And you assume the system's initially at rest. I'm kind of using the mechanical example because the other example is thinking of going over a pothole with your car's suspension system. Certain types of potholes could be like a delta function, right? Give your car a quick snap like that, and then the suspension system bounces around a bit and then decays off to zero. Does that make sense? If it's a really bad pothole, it bends your frame, and then your suspension is different than it was before you hit the pothole. But okay, so you can model any signal. Well, suppose the signal is composed of a bunch of delta functions with time weights alpha. If I apply those to the system, that would be convolving. That would say that y of t would be x of t convolved with h of t. So because the delta convolved with anything is that anything time shifted, that would give me this response right here. So the output of a system, when you fire the input in through the impulse function, gives you the output y of t. In this textbook's notion of how to construct the impulse, or how to construct what we know as the convolution relationship, is to go and say, let's model x as this approximation involving delta functions. So let's say that the true sample values are these weight values here, and we're going to locate those as delta functions on the time axis as an approximation to this integral over here. Because the integral on the top is just, from the sifting property, is just going to be x of t. But if we approximate the integral on the inside, we could write it as a bunch of rectangular partitions if we wanted to. So now we go ahead and take the system's operator on both sides. We apply it to x, and that produces y. And on the right-hand side, we apply the system operator to these individual terms of this approximation, and it goes and sees the function of time there is the delta of t minus nt. So it converts that to the impulse response, only time shifted. And then the amplitude values that sampled x of t come out along with it. And then you take limits as delta t goes to 0 and n delta t goes to lambda. And then you've got your convolution integral. This is kind of hand-wavy, but it's just, I know you've seen this before because you saw this in 3205 probably, at least in 3205. There's other ways of proving it.
What are we proving? Sorry, I didn't get
We're just proving that to get the output of a system, given the input and the impulse response, is the convolution integral. So we're proving this right here. So I'm thinking I don't want to hand out my practice quiz right now because there's only 5 minutes left.
You can take it home.
Well, because I'm so heavy in my excuse this week, I'm thinking of not having a quiz because I'm working so hard on getting my chapters finalized with my editor that my idea was I was going to push to try to get this done today, but this can just be a practice quiz for Thursday. It doesn't really matter to me. I was optimistically thinking I'd try to run it today. Actually, what I thought about doing was letting you take a replacement quiz for the one you just took, and taking whichever one was the better score and replacing it. But this quiz right here is the same quiz I gave last year, and it's not totally secure then in that sense. I'd rather come up with a fresh idea. So this will be a practice quiz. Is that intriguing anybody that you'd like to have a redo, or are you okay to just have a practice?
Some people would.
Pardon me?
Some people would.
Take whichever one it is.
Yeah, take whichever one's good.
So how many people are interested in having a repeat on Thursday versus just having a practice quiz, just to practice and do it in small groups and then report right here in class? Practice versus a redo.
I don't think there's a both.
The quiz won't be, the quiz would probably be what this one is. Well, let me just show you. I'll just give it to you and you can bring it back. Is that safe that I give it to you and you'll bring it back, or no?
When?
Thursday. We'll work it in class if you bring it back. You can just see what I'm talking about for...
So will it be graded or no?
No, it won't be graded. I have to come up with a clean version of it. The question is, do you want me to just look at that as a practice early in the class and then have a redo quiz afterwards?
Yeah.
Yeah.
Okay? Okay?
Take the better listing scores.
Exactly. So to advance the quiz, though, the quiz will probably be patterned after this one, which is based on LTI systems, but it's a convolution problem because, this is a convolution sitting right here. So this quiz had that as the motivation for the convolution. And that just pushes us down the pipe a little bit further is what it's doing. What other questions do you have, since we're basically wrapping up?
So there will be a quiz this Thursday, but it's going to be an either or. It's not a new.
Yeah.
Yeah, it's basically going to involve convolution again.
Yeah. Okay.
But it might involve a convolution of an impulse response and an input as opposed to just two signals.
Well, I
So
think the question was, we're going to bring this back, but then we're also going to take another
yeah, exactly.
to get to maybe make up for.
Yeah, because that's what I picked up from you guys. We'll look at the solution to this one. You can, I'll encourage you to scribble it out right now. Scribble it out before class, and then we'll look at it immediately at the start of class. And then later in the class, we'll have something else. If you got the perfect score, which is true for somebody on this quiz, when I bring up the quiz at the end of the period, you can walk out of here. Or if you got a 38 or a 39 and don't want to take it again, it's totally your call.
Is that solution online too?
No, not for this one. We'll talk about it, yeah. If I post it, I'll post it just before class, just so I can access it. But
Like you're waiting for what else?
okay, thanks.
I could have sworn I saw 39.